Hi there. In this video, we're going to be looking at the divergence and curl of a vector function. So in the previous videos, you would recall that we've been talking about the del operator, and that actually kind of represents the gradient of a scalar function. So if we have the gradient of a scalar function, then what this was day phi day x times I hat plus day phi day y times j plus day phi day z times k. So what we're going to do is we're just going to remove this scalar function and just only write the del operator. So del operator is simply just the change in a certain variable in a certain direction. What we're going to do is take this del operator and we're going to take the dot product with some random vector a, and this a is actually made up of components ax plus ay plus az. And when we take this dot product, you remember that I times I gives us 1 and I times j gives us 0, as is the case with all perpendicular components. Then what we're left with is just simply day ax plus day ay day y plus day az day z. Okay? And this dot product between the del operator and the vector is called the divergence of this vector a. So it's actually written as div of a. So we write it as div of a. So the divergence is defined as the dot product of the grad function with a vector, and we write it as the divergence of a. We can illustrate this with a simple example just to see how it's applied. If we have some vector a is equal to x squared y plus, or rather minus, xyz plus yz squared, then it's just a simple matter of the divergence of a just being firstly the derivative of a with respect to x plus the derivative of ay with respect to y and plus the derivative of az with respect to z. So with respect to x, right, so we find this component ax, ay, az. So we have day ax, day x plus day ay, day y plus day az, day z. So this is simply equal to 2x because of this x squared, y, then minus this derivative with respect to y, so we just get xz, and this derivative with respect to z, we get 2yz. So this is your final answer. So the question you might be asking yourself now is, what does this divergence mean? What is it actually? Okay, well, if we just try to analyze what this equation is actually telling us, it's telling us what is the sum of the rate at which these different components are changing. So what we're adding is the extent to which these different components are changing. So we could think of this divergence of this vector function as indicating the extent to which the vectors are spreading out. For example, if we have the wind blowing in a certain direction, at some point in another room or something like that, if it's still blowing in the exact same way with the same magnitude and same direction, then what this is implying is that the divergence at this point is equal to 0. Okay? It means that there is no change in these vectors with regards to where it is and its magnitude and all of that stuff. But now, if the vectors have changed quite significantly, imagine wind blowing and then it's all going in different directions now, then this divergence at this point of these vectors is a positive number. It's a significant number. It's indicating that the vectors have changed in magnitude and direction. So we can understand this from the mathematical definition. It's simply telling us the sums of the components and how much they have changed. So we can define divergence as being the extent to which these vectors are changing or spreading out. So the next thing that we want to talk about is the curl of this vector function. So with divergence, we took the dot products between the del operator and some kind of vector. With the curl, what the curl of a vector is equal to is the cross product of this del operator and some kind of vector A. So you'd know that when we write the cross product, what we do is we put I, j, and k in the first column, the first row of a determinant, and in the remaining two rows, we put in what we're actually computing the cross product of. So this del operator is day x, day y, and day z. And this vector A is simply ax, ay, and az. So if we compute the determinant of this, firstly we block out the first column and the first row. What do we get? We get day az with respect to y minus day ay with respect to z, and this is the x component, and then minus, we block out the first row and the second column. What we have is day az, day x, minus day ax, day z. And this is in the y direction. We block out the first row and the third column. We get day ay, day x, minus day ax, day y. That's in the z direction. So what is this actually telling us? What does the curl actually mean? In the same way that the divergence told us the extent to which a vector is spreading out, vectors are spreading out in a certain direction, what does the curl tell us? Well, the curl tells us the extent to which a vector is actually rotating. If we think about a cup of coffee, right? If you stir the cup slowly, the liquid inside the cup, it's moving like in a slow manner. But then if we swirl it fast, then you can see that it's actually moving quite much faster and much more, its flow is much more turbulent like that in the cup. So what does that have to do with the curl of A? Well, let's analyze these various components. If we look at in the x, y, and z directions, what we have is rotational motion. If we have, for example, z, y, and x, if we have a vector that is in the x, y direction, and it's rotating about the z direction. So it's like this, and it's rotating. It's rotating about z. Okay? So what actually is changing with respect to it rotating in the z direction? Well, the vectors within the x and y direction. If we look at the z component, okay, an object rotating in about the z-axis, what do we have? The rate of change of this vector with respect to x and the rate of change of this other component with respect to y. So what this is telling us is how these vector components are changing in the xy plane. So what this tells us is how much is this vector changing in terms of its rotation about the y-axis. And then the same thing is applied for the other axis. So if we look at, for example, the y-axis, there's the y-axis or the y component, and there's a vector that's now rotating about the y-axis. So what does this look like? This vector is like this, and the y-axis is carrying on like that. And how is it rotating? It's rotating like this. Something like that, right? So if it's rotating about the y-axis, what are the variables that are changing? Well, the variables that are changing is z and x. So this is telling us how it's rotating about the y-axis. And what do we have? We have rotation changing in the x direction and rotation changing in the y direction. So that tells us how it's rotating in that direction. And the same thing is true, of course, in the x direction. So what this essentially is telling us is a vector. The curl of a vector is telling us a specific vector, and that vector is giving us some information as to how a certain vector field is changing at a certain point in terms of rotating. Is it rotating a lot? Is it rotating a little? And in which direction is it rotating? So that's what the curl of a vector at a specific point is telling us. So we can just compute the curl quickly of just a vector. So we know that the curl of a function is just the cross product between the del operator and some kind of vector A. So if we have A equal to x squared y plus y squared z plus z squared x, and now we compute this cross product. So the curl of A is actually just equal to, we put our determinant I, j, k, and then we write what we're taking the derivative of, so that we write this del operator in the second row. So day x, day y, and day z. And in the third row, we write our vector. So we have x squared y, we have y squared z, and we have z squared x. And what we're doing is taking the determinant. So this is just equal to, block out first column, first row, the derivative of this with respect to y, and there's no y there, so this is just 0, minus the derivative of this with respect to z. And it's just z here, so this gives us y squared, minus, then we block out that first row and second column. Then what we're doing is finding the derivative with respect to x of z squared x, and that just gives us z squared minus then the derivative of this with respect to y. Sorry, the derivative of this with respect to z. So the derivative of x squared y with respect to z is just 0. And then lastly, blocking out the first row and third column, what we're left with is derivative of y squared z with respect to x, that just gives us 0 again, and the derivative of x squared y with respect to y, and that gives us x squared. And of course, we mustn't forget to put our unit vectors in each of the directions. So if we want to compute the curl at a specific point, so let's just say we want to compute it at the point 2, 2, 4. X is 2, y is 2, and z is 4. Then all we'll do is we'll just substitute inside this vector that we've just created. So y squared is 2 squared, and that's 4. So we're left with minus 4i hat. Z squared is just 4 squared, which is 16. That's 16j. And then lastly, plus minus x squared, and then x is 2. So we're left with, again, minus 4k. So this vector that we get is what we get when we compute the curl of this vector at this point. So what that tells us is, at this specific point, this magnitude will tell us how much it's rotating, and this vector tells us in which way in space it is rotating in. So we can actually combine some of these operators that we've just seen. So if we just were to summarize it, if we have a scalar field, and in this scalar field, what we can do is we can take the gradient of this scalar field. So let's just say the scalar field is represented by phi as a function of x, y, and z. Then the gradient of this scalar field is just a vector. So it's del phi, and this is a vector. The point I'm making is that our input to this operator is a scalar, and we get out a vector. So if we have a vector field, we can do two things. We can take the dot product of this vector field, say it's a vector function. When we take the dot product with a vector function, we get the divergence of a, and this is a vector, sorry, this is a scalar. And we can also take the curl. The curl is the cross product. That's the curl of A, and the output is a vector. So can we now take some combinations, right? So we know that the input of the gradient vector has to be a scalar, okay? And now the input of the divergence has to be a vector, okay? So this gradient vector, this del phi, is a vector. So could we, for instance, take one of these operators here, divergence and curl, and then find it off the gradient vector? Well, yes, we can, right? Since the input, for example, curl is this vector A, we can just say replace vector A with this gradient vector. So what happens when we do that? So let's check it out. We take the curl of the gradient vector. So what we've actually done is the cross product of the del operator and the gradient vector. So again, we just put it in like a determinant where we have I, j, and k, and then we have the del operator, day x, day y, and day z, and then this gradient operator is day phi, day x, day phi, day y, and day phi, day z. Okay, and when we take this determinant, what do we get? Let's write it here. Okay, blocking out first row, first column, we get day squared, right? Day and day gives us day squared, phi, firstly with respect to y, and then with respect to z. Then minus day squared, day, of phi, firstly with respect to z, and then with respect to y. I think you can see where this is heading. You can see that it's equal to 0 because why? Mixed partials of multivariable calculus, you'll remember in the previous videos we saw that mixed partials are actually equal. So that minus that is actually two of the same thing, so we're actually getting 0 here. But if we just continue with this, then the second term of the determinant is a negative. And then we block out the first row and the second column. Then we get day squared phi, firstly with respect to x, and then with respect to z. Then minus second derivative of phi, firstly with respect to z, and then with respect to x. Again, you can see that this is also going to give us 0. And then lastly, blocking out first row and third column, what we get is second derivative of phi with respect to x, then with respect to y, then minus, again, second derivative with respect to y, then with respect to x. And this is in the direction of k. So what do we get? We get 0. So what we've done is that we've proved that the curl of the gradient vector is equal to 0. So we can do similar things. For example, we can take the divergence of the curl. Remember that the divergence takes an input as a vector and outputs a scalar, right? So the divergence is the dot product between the del operator and the vector that results when you take the cross product of the del operator with some vector A. So when we do that, what do we get? Well, firstly, this del operator, we write that day x I plus day y j plus day z k. And then this cross product, well, we've already done it just now. So now we multiply. Remember, I times I gives us 1 because we're taking the dot product. So that's very key. We're taking the dot product. And when we do this, we find that we get second derivative of what? Of az, firstly with respect to x, then with respect to y, minus, that's the minus there, times day x of this term here now, day ay, day z, day ay, day z, firstly with respect to x, then with respect to z. Then we can continue out expanding all of these terms, and then when we do that, we find we get day squared ay, day x, day z. Sorry, I've already written down that term. So the next term is actually day squared az, day y, day x, then we get plus day squared ax, day y, day z, then plus day squared ay, day z, day x, and then last term is day squared ax, day z, day y. So it's just expanding out that term with that, and then the last term with respect to that, and then that. So it's fairly simple thing to do. My equations are looking a bit wavy. I apologize for that, but I think you can follow what's going on. And then do these terms cancel out? Well, yes, they do, because mixed partials are the same. So that is the same as that. And then that is the same as that. And then that is the same as that. So again, we're left with 0. So what this means is that the divergence of the curl of A is actually equal to 0 as well. And then lastly, last thing, what we can do is that we can take the divergence of the gradient function. So that's grad of phi. So what we're doing is del operator dot product with del phi. And we can just write this out fairly easily. So the del operator is day x, day y, and day z. Multiplying this by the gradient vector, taking the dot product, I and j is 1, and perpendicular vectors multiplied gives 0. So what we're left with is the second derivative of phi with respect to x squared. Okay? We're taking day x of day phi dx. Day and day, you can think of it as squared. There's the phi and the dx. So it's actually the second derivative of phi with respect to x. And then doing the same thing with the y components, we get day phi, day y squared, and then lastly, day squared phi, day z squared. So this thing is actually given a name, right? So this result is called the Laplacian. The Laplacian. So what it is the divergence of the gradient vector, and it's often written as this del operator squared times, del squared of phi. So there's nothing that's squared here, right? So this 2 is not meaning that this del operator is squared or anything like that. All it means that we perform this Laplacian on the scalar function phi, and when we do that, we get the sum of the second derivatives with respect to each variable.